Raptor engine, without a doubt, has changed the spaceflight industry and will permanently be marked in history for its remarkable performance and complicated simplicity. For clarity, by complicated simplicity, I'm hinting at the minimalism of components being used to produce the record thrust capability. So, it's complicated simplicity in that sense. Buckle up for the facts. Raptor is a family of rocket engines developed and manufactured by SpaceX. The engine is a full-flow staged combustion cycle FFSC engine powered by cryogenic liquid methane and liquid oxygen methalox. SpaceX's Starship system uses Raptor engines in its Super Heavy Lift Super Heavy booster and in the Starship spacecraft, which acts as the second stage when launched from Earth and as an independent craft in space. Starship missions include lifting payloads to Earth orbit and missions to the Moon and Mars. The engines are designed for reuse with little maintenance. The Raptor engine uses methane as fuel rather than kerosene because methane gives higher performance and prevents the buildup of deposits in the engine from coking, which is the heating of coal in the absence of oxygen to a temperature above 600 C to drive off the volatile components of the raw coal, leaving a hard, strong, porous material of high carbon content called coke. Coke consists almost entirely of carbon. The porosity gives it a high surface area, which makes it burn faster, as does a sheet of paper versus a wooden log. When a kilogram of coke is burned, it releases more heat than a kilogram of the original coal. Methane can also be produced from carbon dioxide and water using the Sabatier reaction. The engines are designed to be reused many times with little maintenance. Stoichiometry is the relationship between the weights of reactants and products before, during, and following chemical reactions. Stoichiometry is founded on the law of conservation of mass, where the total mass of the reactants equals the total mass of the products, leading to the insight that the relations among quantities of reactants and products typically form a ratio of positive integers. This means that if the amounts of the separate reactants are known, then the amount of the product can be calculated. Conversely, if one reactant has a known quantity and the quantity of the products can be empirically determined, then the amount of the other reactants can also be calculated. With that explanation of stoichiometry in mind, know that the Raptor engine operates with an oxygen to methane mixture ratio of about 3:6 to 1, lower than the stoichiometric mixture ratio of 4 to 1 necessary for complete combustion, since operating a higher temperature would melt the engine. Think about this. The propellants leave the preburners and get injected into the main combustion chamber as hot gases instead of liquid droplets, allowing a higher power density as the propellants mix rapidly via diffusion. In the staged combustion cycle, propellant flows through multiple combustion chambers and is thus combusted in stages. The main advantage relative to other rocket engine power cycles is high fuel efficiency, measured through specific impulse, while its main disadvantage is engineering complexity. The methane and oxygen are at high enough temperatures and pressures that they ignite on contact, eliminating the need for igniters in the main combustion chamber. The engine structure itself is mostly aluminum, copper, and steel. Oxidizer side turbopumps and manifolds subject to corrosive oxygen-rich flames are made of an Inconel-like SX500 superalloy. The properties of SX500 superalloy, when heated, primarily because of their similarity to Inconel, forms a thick and stable passivating oxide layer, which just means that material becomes passive and less readily affected or corroded by the environment, protecting the surface from further attack. Inconel retains strength over a wide temperature range, attractive for high-temperature applications where aluminum and steel would succumb to creep because of thermally induced crystal vacancies. Inconel's high-temperature strength is developed by solid solution strengthening or precipitation strengthening, depending on the alloy. This is used to manufacture the manifolds and turbopumps of the SpaceX Raptor engine. At sea level, the standard Raptor engine produces 23 meganewtons, equivalent to 5 of 20,000 lb at a specific impulse of 327 seconds or 321 kms at sea level and 350 seconds 34 kms in a vacuum. Specific impulse is a measure of how efficiently a reaction mass engine, such as a rocket using propellant or a jet engine using fuel, generates thrust. For engines like cold gas thrusters, whose reaction mass is only the fuel they carry, specific impulse is exactly proportional to the effective exhaust gas velocity. A propulsion system with a higher specific impulse uses the mass of the propellant more efficiently. In the case of a rocket, this means less propellant needed so that the vehicle attached to the engine can more efficiently gain altitude and velocity. Raptor vacuum, used on the Starship upper stage, is modified with a regeneratively cooled nozzle extension made of brazed steel tubes. increasing its expansion ratio to about 90 and its specific impulse in vacuum to 380 seconds equal to 37 kms. The main combustion chamber operates at a pressure of 350 bar 5 100 psi, exceeding that of any prior operational rocket engine. The Raptor's gimbaling range is 15, higher than the Space Shuttle main engine RS-25's 12.5 and the Merlin's 5, though most Raptors on Starship are incapable of gimbaling. SpaceX has stated they aim to achieve a per-unit production cost of $250,000 upon starting mass production. With regards to development, in November 2012, Musk announced that SpaceX was working on methane-fueled rocket engines, that Raptor would be methane-based, and that methane would fuel the grandiose Mars colonization effort. The atmosphere of Mars is primarily composed of carbon dioxide at 95%, molecular nitrogen at 285%, and argon at 2%. It also contains trace levels of water vapor, oxygen, carbon monoxide, hydrogen, and noble gases. Because of the presence of underground water and carbon dioxide in Mars' atmosphere, methane, a simple hydrocarbon, could be synthesized on Mars using the Sabatier reaction. The Sabatier reaction, or Sabatier process, produces methane and water from a reaction of hydrogen with carbon dioxide at elevated temperatures, optimally 300-400 C in pressures, perhaps 3 megapascals in the presence of a nickel catalyst. NASA found in situ resource production on Mars to be viable for oxygen, water, and methane production. In space exploration, in situ resource utilization, or ISRU, is the practice of collection, processing, storing, and use of materials found or manufactured on other astronomical objects, for example the Moon, Mars, and asteroids, that replace materials that would otherwise be brought from Earth. ISRU could provide materials for life support, propellants, construction materials, and energy to a spacecraft payloads or space exploration crews. It is now very common for spacecraft and robotic planetary surface mission to harness the solar radiation found in situ in the form of solar panels. The use of in situ resource utilization for material production has not yet been implemented in a space mission, though several field tests in the late 20s demonstrated various lunar in situ resource utilization techniques in a relevant environment. In situ resource utilization has long been considered as a possible avenue for reducing the mass and cost of space exploration architectures, and that it may be a way to drastically reduce the amount of payload that must be launched from Earth in order to explore a given planetary body. According to NASA, open quote, in situ resource utilization will enable the affordable establishment of extraterrestrial exploration and operations by minimizing the materials carried from Earth. End quote. In early 2014, SpaceX confirmed that Raptor would be used for both first and second stages of its next rocket. This held as the design evolved from the Mars Colonial Transporter to the Interplanetary Transport System, the Big Falcon rocket, and ultimately Starship. The concept evolved from a family of Raptor-designated rocket engines from 2012 to focus on the full-size Raptor engine of 2024. In January 2016, the United States Air Force awarded an OTA award other transactions award of us $33.6 million development contract to SpaceX to develop a prototype Raptor for use on the upper stage of Falcon 9 and Falcon Heavy. According to Washington, the U.S. Air Force has provided SpaceX with an additional $47 million to support continued development of the company's Raptor engine. A Defense Department contract announcement in October 9 stated that the Air Force was modifying an existing agreement with SpaceX, originally awarded in January 2016, by providing the company with $4766 million for the development of the Raptor rocket propulsion system prototype for the Evolved Expendable Launch Vehicle program. The statement did not include additional information about the nature of the work, other than that it would be completed by the end of April 2018. The work, according to the announcement, would be conducted at NASA's Stennis Space Center, which hosts engine testing for the Raptor, as well as SpaceX's headquarters in Hawthorne, California, and Los Angeles Air Force Base, home to the Air Force's Space and Missile Systems Center. Apologies for the legislative emphasis there, but it's essential. Stick with me. The Super Heavy booster has 33 Raptor engines, and Starship has 6 additional Raptors. From an economic standpoint, the current integrated variant of the Raptor engine series costs $1 million each. That sums up to $39 million for the engines on integrated flight tests. The first version was intended to operate at a chamber pressure of 250 bars 25 MPa, 3600 psi. As of July 2022, chamber pressure had reached 300 bars. Each engine requires a heat shroud to protect pipes and wiring from engine heat. There are 3 versions of the Raptor. The Raptor Vacuum is the dedicated deep space propeller. Raptor Vacuum RVac is a variant of Raptor with an extended, regeneratively cooled nozzle for higher specific impulse in space. The vacuum-optimized Raptor targets a specific impulse of approximately 380 s or 3,700 meters per second. A full duration test of version 1 of Raptor Vacuum was completed in September 2020 at McGregor. The first in-flight ignition of a Raptor Vacuum was on S-25 during the second integrated flight test. Raptor 2 because it was the second iteration. A NASA employee standing between two Raptor 2 vacuum engines as seen in the background and a Raptor 2 sea-level foreground. The streamlined design is due to the reduced parts visible above the engine nozzles. Raptor 2 is a complete redesign of the Raptor 1 engine. The turbomachinery, chamber, nozzle, and electronics were all redesigned. Many flanges were converted to welds, while other parts were deleted. Simplifications continued after production began. On 10 February 2022, Musk showed Raptor 2 capabilities and design improvements. By 18 December 2021, Raptor 2 had started production. By November 2022, SpaceX produced more than one Raptor a day and had created a stockpile for future launches. Raptor 2s are produced at SpaceX's McGregor Engine Development Facility. Raptor 2s were achieving 230 tons or 510,000 pounds of thrust consistently by February 2022. Musk indicated that production costs were approximately half that of Raptor 1. Raptor 3, named because it was the third iteration. In May 2023, Musk reported a successful static fire of a Raptor 3 to 350 bar 5 100 side for 45 seconds, producing 269 tons of thrust. In October 2021, SpaceX initiated an effort to develop a conceptual design for a new rocket engine with the goal of keeping costs below $1,000 per ton of thrust. The project was called the 1E337 engine, to be pronounced LEAT after a coding meme. Although the effort was halted in late 2021, the project may have helped define an ideal engine, and likely generated ideas that were incorporated into Raptor 3. Musk stated then that, "We can't make life multiplanetary with Raptor, as it is way too expensive, but Raptor is needed to tide us over until 1337 is ready." Subscribe to us at SpaceX front page. Join the community, we have plenty of aerospace insight coming up. Just imagine what Raptor 4 or 1337 will do whilst you watch this video next. On the historic launch of Integrated Flight Test 3, which showed the world just how powerful the Raptor 3 engines are as they launched Starship higher than it has flown in history.